Hello everyone, this is Sustainability Modeling, Spring 2013, lecture number 1. It's primarily an introductory lecture to the class. Let's see what the contents of this lecture are. I think I'll tell you a little bit about this class in more detail, besides what you may have already know. We'll look at some sustainability concepts and a little history behind the whole concept of sustainability and the reason for modeling within the sustainability context. So we'll do a little bit of understanding of why modeling, and specifically why modeling sustainability, and we'll go through some initial examples. So let's start with talking a little bit about this class. The rationale for the class, why this new class was started. I want to tell you a little bit about that. We'll talk about the syllabus, which you've already seen. Some of the class logistics, being that this class is being taught for the first time in this format. Some of the tools that we'll be using. So let me tell you a little bit about the rationale. This class is essentially experimental in nature. This is the first time that the class has been taught. Is the first time that the class is being taught in this purely online format and in an open format. The philosophy of this class is what I call modeling for non-modelers. So it's really about bringing up participants in the class to modeling skills that are introductory in nature, of course, but that will be sufficient for people to understand modeling and what models do and what models don't do in the context of sustainability. We use sustainability really as a means and not an end. So this is not a class on sustainability. It's more, to be completely honest, it's more using sustainability as an excuse to teach modeling. So it's and I think sustainability offers a lot of qualities because of the integrative nature that make it an amenable topic for modeling. So it's really about it's more a class about modeling and using sustainability issues for modeling purposes. And I think the overall gist of it is that I expect and we expect that this could become a contribution to the evolving field of sustainability science. I haven't seen any other modeling class that has the scope of this class, and that's part of the reason why I created the syllabus and the class itself and the topics, because I haven't seen out there a class that really covers not only the topics, because the topics you will see them cover in more traditional sustainability classes, but from the modeling standpoint, I haven't seen anything like this. So actually, if you do see a class like this, I really like to know, because I did a fair amount of research trying to find similar classes elsewhere, so as to not reinventing the wheel, which we're pretty much going to be doing in this class. So hopefully that'll give you a little bit of an understanding of what the class is about. Let's move on to the syllabus. The course synopsis that I put in, I hate these wordy slides, but I just wanted to capture some keywords in the course synopsis that I offered in the course syllabus that was circulated earlier. Really, this class it's for students who are concerned with sustainability issues. Okay, so that's it's first and foremost the first interest has to be on sustainability issues. You can get a modeling class in other topics elsewhere. So this is going to be a modeling class on sustainability matters or issues. And we're going to be honing in on understanding what modeling can do to help solve sustainability problems. Okay, so modeling is going to be a tool to solve these problems. We're going to be focusing very much on quantitative understanding. So this is really a class about crunching numbers and understanding what these numbers mean, and understanding where these numbers come from, and understanding the way these numbers are arrived at, how they may vary under different assumptions. And A lot of the modeling is going to be directed at designing, policy measures. So it's really, uh, you know, one nice feature of the way I've tried to design this class is that I want to go from the modeling and from the mathematics and number crunching to really cross the bridge to designing policy measures that affect these sustainability issues. To do that, we're going to be using something that's been around for a few decades, at least in formal form, which is system dynamics or system dynamics theory. And I'm going to be using tools that will allow you to get hands-on knowledge of these tools and how they're used. My aim with this class is that it's a class that's open to students of all backgrounds. So it's not for students that have a purely a scientific or natural science background or purely policy background or purely modeling background. I think it's a class that has mass appeal, and hopefully that'll be the outcome. So let's see if we can get there this semester. It'll be very, very interesting. Let me move on to the learning objectives. These are also detailed in the syllabus, but I wanted to highlight and explain a little bit of what's behind them. I think, first and foremost, it's about introducing students to key issues in sustainability, not isolate them and in of themselves, but actually how they interact with each other. So this is really about understanding these interactions and understanding them at different scales. And we'll look at issues that go from local to regional to global scales, and different issues will be approached from any of these scales. I think the next piece is that we're going to be analyzing these interactions from, again, quantitatively. We're going to be focusing on really on number crunching quantities, and trying to understand what's behind these numbers. We're going to be using models to handle interdisciplinary data. This is data that comes from different disciplines in sustainability, and using system dynamics modeling as a tool for this integration of data. I think one piece that hasn't been mentioned and I wanted to emphasize is also to understand the limitations of these models and these tools, not only because of assumptions that we make, but also because there's a lot of uncertainty in the data and in the issues themselves. So I think again, we're going to be trying to quantify what this uncertainty is. At least it's one thing to know that you don't know something, but at least if you don't know what it is, but you do know that it's within some uncertainty range, then you have a much better idea of how to handle it. And we're going to be, looking at this with a series of examples in a series of topics. Okay, so that's sort of the the learning objectives, looking at the interaction, quantitative, interdisciplinary, system dynamics modeling, and uncertainty. I detailed the lecture topics a little bit more in the syllabus, but I wanted to sort of go through them and just to so you get a picture of what we want to cover and how ambitious this syllabus is. So today we're talking about what this course is about. So that's today's lecture. Next week we're going to be looking at modeling and water models and how they are used and how they're structured and what do they require. So a little bit of the sort of science and the art behind modeling. So we're going to be doing that next week. Then we're going to focus a little bit more on the tools that we're going to be using for modeling. So that's the system dynamics piece of it, and that's lecture 3. Lecture 4, we're going to be looking at the issue of population, which it's a key variable that drives sustainability, as we'll see, starting today. Population is a key variable to understand, um, how is it that we can become sustainable or not, and what are the issues and criteria that point in one direction or another. Um, um, Lecture 5 has to do more with social interaction. So, once we look at population as a variable, as a quantity, then we're going to be looking at how people interact with each other and what those dynamics are. And so it's more like the social, the modeling of social dynamics, so to speak. Um, and a key variable that is used to understand dynamics within a population, dynamics of sustainability, is economics. So this is not a class in economics, of course, but we will introduce some economic concepts to try to understand how is it that we make some decisions, and what types of decisions are economically feasible, and in addition to be socially feasible and politically feasible, and other aspects that we'll be covering. Um, um, then we're going to focus on a very early study that we'll start mentioning today, which is the essay on the principle of population by Thomas Malthus. And we're going to be looking at that today, a little bit historically, introductory, but we're going to focus more closely on what I would call the very first formal piece of research or investigation on sustainability that was done in the 18th century. Um, then we're going to look at what are the mainstream sustainability issues, climate and climate change being one of them, and see what challenges does that pose to sustainability, and how does it shake things up. Um, Climate is one, water is the next. Water is a key resource that sort of cuts across a number of activities that human beings are involved in, and certainly has a big impact on sustainability matters. Um, Energy is another one. Energy is a big factor affecting how humans interact, and it drives a lot of policies in other areas, including economics, including water. And you can see how some of these topics start touching each other. It's really difficult to talk about climate without talking about energy, or talk about water without talking about energy and climate. You could start seeing that these issues are not really isolated, but we're going to try to start integrating them into some common framework. Um, Food and food security. It's a big sustainability issue. Actually, it's probably the issue that started much of this sustainability and sustainability science. And we're going to be looking at food and food security issues. Biodiversity, and that's also another topic that we're going to be looking at, and from more ecological and environmental standpoint of sustainability issues. Um, we're going to go back to a key study that we'll also introduce today. This the a famous study that was done in the 1970s, the Limits to Growth study, which we'll introduce today. And we're going to go back and analyze that from once we learn some more specifics about all these different activities and sectors of human activity: water, energy, biodiversity, climate. We're going to be coming back and looking at the limits to growth questions and hypotheses. Um, and then, towards the end of the class, at the end of the class, actually, we'll look at some of the issues I had. How can you take this forward? How can you take the learning in this class, to the next level, and what this can do for you? So, in a nutshell, those are the lecture topics. Approximately each of these will be a weekly lecture. I may merge, depending on time, one or two of these into the next, but I view these as sort of independent topics that will deal once weekly. So that's a little bit of the plan. Something that probably will interest you is how this class is going to be graded, and I do detail that in the syllabus. And essentially the class is going to be graded by two major assignments. One's going to be a paper review, and this is going to be, I'm going to give you a piece of literature, and I'm going to ask you to critically review it in what I call a journal style of fashion, and we'll look at what that means, and we'll give instructions and indications. And then the other piece, the other major piece is a paper or a poster in conference format, which we'll detail later. But essentially, either a written paper or a poster that you could hypothetically present at a conference, or you actually may end up presenting at a conference if the opportunity arises. I'm going to be looking, in addition to these two formal assignments, I'm going to be looking for a lot of class participation. This class is only it's going to be a lot more fun for you and for me if you guys participate. And to do that, we've created a forum for essentially continuous discussion. So this is not the fact that we have a Facebook page allows us to essentially have a 24/7 discussion forum for the class, which I think is going to be very interesting. I'm going to be looking at the forum all the time. I'm going to be looking at any comments, questions you have. I'll do my best to answer them quickly. But what I like about having this discussion page on Facebook is that it allows everybody to have access to the same information in real time. This minimizes any delays. There's no, I missed the class, I missed the discussion, I didn't understand what was said. It's because it's going to be written, it's going to be sequenced in real time, and it's going to be dated. So it's going to be very, very, much more accurate. So hopefully that will be very helpful, and a mechanism that we are experimenting with in this class. I also wanted to mention that one of the things that I like to do in the class is to encourage participants in the class, essentially, to post. Also use the group's Facebook page. Use the Dropbox folders for the class to post materials. If you come across anything that you think is relevant to the topics that we're covering, that we've missed, that we haven't seen, that you find interesting, you just do a quick posting on Facebook, on the Facebook page, and we'll have access to it. If it's a material, we can upload it on the Dropbox site for everybody to have access to. It's a very, very efficient, real-time mechanism to share information, and I think I want to encourage people to really use it, not just by consuming information or consuming what's there, but actually, if you want to contribute to it, you're more than welcome and encouraged. So I want to put that out there as well. Okay, so that's a little bit about how we're going to be grading the class. I want this to be a very participatory process from the individual standpoint through your assignments, and also from the collective standpoint through your contributions to the media that we're using. Okay, let's talk a little bit about class logistics. As you probably have surmised already, the lectures are fully online. There will be no in-classroom meetings. So there's no meeting in a classroom, no sitting in a table in front of me, in front of others for whatever it is, an hour and a half or 3 hours a week or whatever it is. So it's going to be primarily this media that we're using to share is what we'll do. Okay. The lectures will be recorded and posted on Mondays or sooner, over the weekends, but certainly by Mondays, for viewing on Facebook, on the Facebook class group page, and also in the Dropbox folder. These PowerPoint shows will be both on Facebook, that you can see them, but also on the Dropbox folder if you care to download them and then watch them, offline or whatever it is. Okay, so that's one that's one mechanism. The instructions for the assignments, for the review paper and for the poster or the conference paper, all the instructions, the contents, the requirements, the deadlines, the delivery mechanism will be posted as well on the Facebook Dropbox combination. Okay. And I think one important thing that I want to indicate to all of you is that we should make use of the Facebook mechanism to communicate. And like I was alluding to before, it provides a very powerful mechanism to essentially share information. So unless there's something extremely private that you want to communicate to me, which you're welcome to do, and you can use my email address, which is on the syllabus, it's going to be more time efficient
you know, some of the questions you may have may may already have been asked by someone, and maybe it's already on the Facebook page. So in order to save time and to embrace this collaborative approach to learning, I want to encourage all communications to be handled through the thread discussions on our class Facebook page. Okay, so again, unless it's something extremely private that, you know, of course, you wouldn't want to share with everybody else, and I envision those will be minor opportunities. Everything else should be communicated through our Facebook page. Okay, so we'll do that. So, given that overall approach, let's talk now a little bit about sustainability. And it's you've probably taken another class on sustainability. If you haven't, I thought it would be a good idea anyway to try to define what sustainability is. And so sustainability is, and I picked up a few definitions that I found on dictionaries and on the web. The capacity to endure. Well, it's kind of a general definition, which is fine. Probably not my favorite. Um, a more traditional one that I found was a method of harvesting or using a resource so that the resource is not depleted or permanently damaged, which starts getting at the relationship between using a resource and the state of the resource in the future. Okay, and that's a little bit of what I want to talk about. Um, Now, the definition that I found: the quality of not being harmful to the environment or depleting natural resources, and thereby supporting long-term ecological balance. Again, you can start seeing a couple of emerging things here. One is the use of a resource, and second is it's the time issue. How what are going to be the impacts of that use into the future. The definition I sort of continue to like the most is the definition that was put forth by the United Nations in the late 80s, um, which sounds something like meeting the needs of the present without compromising the ability of future generations to meet their own needs. So I think the key items that need to be captured here is that there is a relationship between resource use in the present, resource use in the future, and satisfying needs in the present and in the future. And the balance of all that is what it's this concept, this elusive concept that we refer to as sustainability. So it's not a static concept, but it's a concept that has evolved over time and that will continue to evolve over time. Okay. Um, so I want to do a little bit of history, and I want to look at the work that I consider to be the sort of the first attempt to formally pose the questions of whether humanity, our world, our lives were sustainable in a more or less quantitative fashion. So it's not just about posing the question. That tends to be posing questions, and in the context has been done, but posing questions and trying to answer them in a quantitative way has not been done that frequently, particularly not in sustainability. And the first of those works was the work of the Reverend Thomas Malthus, and we'll talk a little bit about that, about Malthusian analysis. Um, we'll look at the historically what followed that in the agricultural agrarian revolution that took place, and I'll tell you a little bit about that, and we'll look also at that a little bit more detail later on when we discuss food production. Um, the the issue of the tragedy of the commons, which was a piece of seminal work that came about that really tackled um, uh, the the notion of the use of a common resource, and the different approaches that can take. And that was a very interesting piece of work that was published in the late 1960s, based on some historical data that had been gathered for a couple of centuries. Then we'll talk a little bit about
the study in the 1970s that it would be probably what I would call the first attempt to look at sustainability from a modeling standpoint. So not just quantitatively like Malthus did, but actually, using computational models and system dynamics tools. And this was the limits to growth study that was published in the 1970s. And then we'll move on just to introduce some of the, what I call the today issues, and we talked a little bit about these in the syllabus: water, food, energy, and the economy. So let's move on to the study of the work of Thomas Malthus. Thomas Malthus was a reverend who in 18th century, well, late 18th century, beginning of 19th century England, published a series of works that became known for his concerns about population growth and sustainability. So I would say that this is perhaps the first work to tackle what we know as sustainability today, and I think that's fairly accurate to say this. He authored the essay on the principle of population, and there were 6 editions of this report or this essay that were published between 1798 and 1826. And Malthus' central issue was the unequal nature of food supply to population growth, or our ability to produce food to feed the population as it was growing. This of course centered in what we would call today the exponential or geometric growth versus the linear or arithmetic growth. If you think about it very simply, let's take a look at a couple of graphs. The first graph just sort of shows what exponential growth looks like versus linear growth. And exponential growth, essentially, it's growth that is multiplied or that's dependent on the number of population that's present. So let's say, very simply, if at the very beginning there was one person, this person, or actually there should be 2 people so they can reproduce. They have a number of children. Let's say they have 2 children. So the first generation produces 2, but each of these 2 is able to produce 2 more. And then what you start having is that you have an accelerated growth curve, which is the blue curve there on the left. That's referred to as exponential, and that is referred to population. Malthus argued that food production was at best going to be able to follow a linear growth model, meaning that it will essentially, if technology in food production would allow food to grow over time, such that the amount of food produced per year would increase by a constant amount. Okay, so that was Malthus' assumption, and that's what's called linear food production or linear growth for food. So Malthus' concern was that essentially we're going to be running this into a situation where even if like the growth, if you look at the curve on the right, even if the linear curve it's for time, it's higher than the exponential curve of population. At some point, the population growth was going to overtake our ability to produce food, and we would crash. So that was essentially the concern. Now this concern today we understand that was driven by the assumption that food production would follow this linear growth model. And what's interesting, it was published in 1798, and I have here a little picture of the cover page of the original study, but you can actually see the whole study in some of these links. The first 2 links cover the entire essay. The third link there that I encourage you to see is a nice summary of the history and what, how that study by Malthus was actually, taken up by the how it was criticized and what happened with it over time. So now, needless to say, Malthusian analysis and the Malthusian predicament um, um, was sort of, it had a high impact when it happened, in the beginning of the 19th century. But then this agricultural revolution sort of came about, and what started happening is that there were changes introduced around the world in the 18th and 19th century that allowed agriculture and food production to grow at a much faster rate that Malthus had predicted. So um, this created sort of a backlash um, towards the Malthusian predictions, the Malthusian judgments that that population was going to overtake food production, and we're all going to die, that the world had no future, and we start living for a couple of centuries, start living in ages where that saw a lot of progress. Um, and a big part of that progress was in food production and this agricultural revolution. The changes that were introduced were, anything from new crops to rotation of crops, so you could use the same piece of land and have several harvests of several crops during the year, so as to keep production going. It was not just a bimodal in which you would grow part of the year and then the rest of the year not. Um, the introduction of new and improved breeds of crops, um, infrastructure, better buildings to store and to conserve food, drainage purposes, better ways to have irrigation, more efficient irrigation, so that the per land unit production of crops could grow. The use of fertilizers, new implements became new. Um, you know, became new ways to accelerate food production. So this had backlash on the whole Malthusian theory that was based on essentially the fact that food production was tapped out, or the rate of food production was tapped out. This agricultural revolution demonstrated that, essentially innovation and improvements could really turn things around and ameliorated that concern of population. Um, and this actually revolution, went well into the 20th century. And especially in the 1960s, there was a sort of another big expansion with high yield varieties of cereals and more irrigation, better irrigation infrastructure, better management, synthetic fertilizers. So the chemical industry took off and really created this uh, powerful growth of food production that really, through the predictions that Malthus had made at the beginning of the 19th century, completely away, because there were about 100, 150, 160 years went by where the world saw a really large growth in the food production, and completely quelch these concerns of competition with population growth. Um, so that sort of went away, and I think what happened as a result is that population growth really took off exponentially. And if you look at that population growth curve, the exponential, you can see that as time progresses, the slope starts getting steeper and steeper. So we really started growing as a population very, very fast. So this gets us into the 1970s or thereabouts, or sort of the 60s and 70s, when we started looking again at the data and saying, yes, population is growing very fast, and yes, food production has also grown fast, and we're going back into a situation where we should start thinking about how to balance these two. And it was interesting that for over 200 years of history, sustainability was the competition between population growth and food production, and you know, we'll see today, and we'll start seeing in this class that there are a whole host of other issues that are involved. Now, this late 60s to the tragedy of the commons, and you know, this is a study that was published in 1968 by a let's see, the classical paper by Harding in 1968. But actually, the studies was conducted, or the this work focused on villages in England before 1750, and in those days, these villages had large nearby areas that belonged to the village. Okay, and these common areas were not held in any sort of private ownership, but members of the village could raise their sheep on their land, and also and often released their extra sheep to the commons. And the idea was that you know, I'll feed the sheep with my resources, but there's a common pool also that I can use, and there's really no one stopping me from doing it. Um, so these users reasoned that even if their animals on the commons did not grow well because of overconsumption of the grass, any growth was a benefit that would have not otherwise have materialized. So whatever happened outside in the commons was extra. But what happened is that if everybody starts doing that, and everybody starts consuming from the commons um, in an uncontrolled and uncoordinated way, then the outcome of that, and that's what Harding shows in his paper, is that essentially this results in the collapse of the commons and essentially the death of all the sheep. So it's called the tragedy of the commons, and it was an interesting study because it gave some theoretical basis to the approach of use of resources by individuals in different ways. In a sort of an individualistic way, you know, every person on its own, or in a collective way in which, and this started putting some theoretical meat on the science of sustainability, so to speak. So I would say that, you know, in addition to the work by Malthus, then this tragedy of the commons work was a second major piece, and it took up, you know, like I said, took a couple hundred years to get from one to the other, almost 170 years actually, to get from one to the other. Now there's a nice video that I encourage you to see, and I'll let you watch that on your own. I'll post this video as well on our YouTube page that has a very nice explanation of the issue of the tragedy of the commons that I encourage you to see. And we're going to come back as well to this when we discuss economics and social behavior and how we model that. Okay. The next piece of work has to do. It was very shortly thereafter. From the tragedy of the commons work, and was the limits to growth publication. And this was a study that was commissioned by the Club of Rome, which is an international think tank that was founded in the 60s, and it's still in existence today. And it was really the first study of its kind, in that it attempted to computationally simulate global sustainability issues. So to me, this is the Limits to Growth study of 1972, the first edition, became this was essentially 40 years ago. It became the first attempt to try to simulate what would happen in the world under different scenarios of growth. Okay, and to use this, the researchers developed a model that was referred to as the World 3. I have never quite found out if there was ever a World 1 or 2,
But all I know is that there's model World 3 that actually still exists, and I'll tell you a little bit about it today. Um, the study became quite controversial because um, I think, unfortunately, and this is just my opinion, I think it focused more on the policy implications. So only the outside of the study got a look. Okay, so I think people sort of read, how like, what I like to say, people went straight to the conclusions of the report, read only those couple of pages, and then never really stopped to understand what was behind it. And I think that there was a lot, that the most valuable piece of work, and the reason that the limits to growth, in my opinion, has had such an impact, and probably the reason that no other study to date has had that same impact is because of what was inside, the methods that were used, and the potential for it. And um, much of what we'll be learning in this class has its roots in the science that was developed for this limits to growth study. Um, Now, interestingly, and we'll see that in this class in a few lectures time, this study was followed by what was referred to as a 30-year update. So the same scientists sort of got together in 2000 or thereabouts and looked at, well, so we predicted 30 years ago this was going to happen. What has actually happened? And then try to see what was right and what was wrong and why, etc. And actually, it turned out that a lot of the trends that were identified were right on the money, and we'll talk a little bit about that. Um, so I want to talk briefly some more about the World 3 model, because it's really it's the kind of tool that we're going to be looking at. We're not going to be simulating the whole world. We'll probably tackle some more specific issues, but the science that's there, it's really the kind of approach that we'll be using, with the corresponding updates that have taken place over the past 40 years. But this model essentially used a set of five quantitative variables to understand what was happening in the world and what would likely happen in the world under different scenarios. And the first variable is population. Okay, so these are quantitative variables. So these are variables that uh, can be quantified and can be used to understand the state of the world. So population of the world is one key variable that tells us where the world is. Capital is another variable. This is the sort of the amount of capital. This has to do not just with money, but also with infrastructure, services, and the amount of capital that exists in the world. Food, okay, again, we go back to food production as one of the key variables that drives sustainability. The state of non-renewable resources, okay, and how use of these resources uh, to live and to produce capital and to generate food and to grow population is used. And um, and then a side effect of growth, which is pollution, and the limit to growth study, the World 3 model, had sort of a pollution variable in there to account for the fact that population growth and capital growth and food production and resource depletion led to um, a measure of degradation of the surrounding environment, which was referred to as pollution. So those were the five variables that were used in this study. Okay, so let me show you just typically what the output of this model looks like, and I hope the curves are clear, but you can see in the graph there are five curves, and there's a time horizon between 1900 and 2100. So what they did was that they looked at what had happened in the world between 1900 and 1970, which is where they cut off the data um, um, to develop the models. And then they looked at
what would happen between 1970 and the next 130 years until 2100. Okay, and they have these five variables, and you can see here essentially how each of these variables behaves, and I just have some snippets as to how these variables behave. The first one is that the limited resource pool is exhausted. So you can see that the resources curve drops between abundance in 1900, or that was the starting resource pool in 1900, and then in 200 years you essentially consume all the resources. You can see that that food production grows essentially at the beginning due to resource availability. So there's resource available, there's technology, so you can use water and you can use energy to produce food. But after these resources start being depleted, then the ability to produce food decreases, and that's sort of the collapsing part of the system that this study shares with the work of Malthus. Um, Population also can grow because of resource and the food availability. So there's resources, there's food production, so people can grow. But of course, when resources start running out and food production starts slowing down, then population also starts decreasing. And industrial pollution industrial output and pollution pretty much follow the same trend. There's a while there's resources and there's population, industrial output, this capital will grow. There'll be more machines. There'll be more production of other things, but that generates pollution, and and both of those grow, of course, as again because the resource pool is being shut down and the resources go essentially decrease to a point where there's pretty much not available anymore. Eventually capital output and pollution itself, die away. There's a little bit of a lag on pollution because the underlying assumption here is that um, pollution probably takes some time to develop or at least to be noticed in the system. So that's the overall gist of it. So this is the kind of thing, the kind of analysis that this World3 model allowed to do. It allowed to look at these five variables in an interlocking relationship with each other. So these variables don't operate independently. They are very much interactive with each other, and how the collective of the five of them would evolve in a period of 200 years. Okay, so that was the value um, that I see in this study. Unfortunately, as I said, I think people focused more on the sort of the 2100 result and saying, oh, so you're saying we're all going to die, that food's going to go away, population is going to go away. So so that's sort of the it's like Malthus. It's sort of discredited, or people didn't pay too much attention to it. But there's a lot of value in how in tying these variables together and seeing how they interacted. Um, the nice thing about models, and the World3 is no exception, is that it allows us to look at what if scenarios. What if we started with a world that had twice as many resources as we have now. So, what would that do? And essentially, so let's say an example is, what like it has happened. What if we discover more oil reserves, or we have better ways to access groundwater and minerals? Okay, um, so there's more resources, and in this particular simulation of the model, there were twice as the base simulation that was presented before, so more resources. And essentially, what happens is that the resource availability actually delays the decreasing limb of population. So it's still, even if you have twice as many resources, and that's what the model simulated. Even if you have twice as many resources, um, you end up in a situation where
resources are going to be depleted. Of course, they get depleted later on, so there's a delay. Um, but nonetheless, if there's a delay in resource availability, there'll be also a decrease in associated population, food, and industrial output. Okay, so it's sort of the same finding. It's just that it happens later because you have more resources. It's like having more money in your bank account and then losing your job. You're going to be able to sort of live off longer, but eventually, if you don't find a job, the situation won't be sustainable. So that's a little bit of the same assumption. Um, and Now, in this particular case, resources are not wiped out completely. You can see actually that at the end, the resource pool sort of picks up, um, but it is severely depleted compared to its initial abundance. So this scenario, twice as many resources, indicates that you're still headed for an unsustainable output or outcome, um, but it just happens later. Okay, so that's sort of the 5-second version of it. So, well, then they push the envelope even further. So, what happens if we have a world with unlimited resources? This means that resources um, are there. You have a vast pool. Okay, um, and in this case, you essentially you have sort of infinite resources, but they're still consumed. So you're still consuming them. Um, and Now, what happens if you have infinite resources is that you start. This is where the trade-off comes in. If you have infinite resources, you're able to produce a lot more food. You're able to produce a lot more industrial output. Population is able to grow more, but then pollution takes off. So you generate enormous amounts of pollution, and then that in turn um, affects because it increases the death rate of population. So if there's more pollution, the assumption is that more pollution will affect population growth because it will increase the risk of death of population. People will get sick because the water is polluted, the air is polluted. Um, so population actually is indeed affected by it. And and look at the industrial output and food production towards the end, where they really start increasing. I want to ask you to think about that and answer why that happens. I want you to comment on the group page on that question. Okay, you got to think a little bit about this dynamics, but I want to more intuitively try to make you think about this. Okay. Well, then they looked at a whole variety of scenarios. So they had a world with unlimited resources, but pollution control. So this is a world where the resource pool was very large and there were pollution controls. So pollution could not go above certain value. So there was maybe a technology or some technological innovation that would allow uh, for for pollution to be kept in check. Um, so essentially, the outcome of this is that the population grows more, the food availability becomes scarcer because now you have population growing uncontrollably because there's nothing to impede it. There's plenty of resources, there's plenty of food because you can produce it, but as population starts growing, it will overtake food production capability. Um, and then as you consume these resources, then it becomes harder to produce industrial capital output, and eventually things go down. And pollution eventually, I mean, it will the fact that it's controlled doesn't mean it doesn't happen. It will occur, but it'll just occur much slower. Um, and and then there's another scenario at the right, which is the same, unlimited resources, pollution controls, but then increased agricultural productivity. So this is the scenario in which you're able to produce more food with the same resources. Okay, it essentially sort of exacerbates these trends. So it's sort of the same, a little bit of the same output. It's just that it's a little bit more accentuated these trends. So what happens if you have unlimited resources, pollution controls, and now you have birth control. So you have a way to control population by regulating the birth rate of population. Okay, that's the scenario on the left. And the scenario on the right is the same, but it has the increased agricultural productivity, so more food production. So the outcome of this is that because population is controlled, um, food production and industrial output per person grow very fast. But then pollution also, it's even if you have it controlled, it will grow because you're generating more food, you're generating more output. Industrial activity generates pollution, um, and essentially all this growth of food production and industrial production drive down resource availability. Okay, so essentially resources are depleted in both cases. Um, and then the nice thing is that you can start looking at all these different scenarios, and these two I think are a little bit unrealistic because these are scenarios in which you have what's called a stabilized population. So this is a situation where um, by some magical rule you're able to say, okay, so we will grow world population to this level and stop. Okay. Um, but it's useful to just look at the outcomes, and the outcomes of this, it's that um, the pollution is kept in check, because the growth is limited, but the ability to produce food is limited by resources, and so that's another um, another outcome of this. And both are pretty much the same. Um, then they looked at what's called a stabilized world model, and again, stabilization is brought about by controlling population, which I think is completely unrealistic. Um, and Now industrial output and food production are kept efficient over time, and and independent of resources and better technologies. So that's a piece of it. Um, Now, by depleting less resources, then pollution is kept in check. But again, these are sort of unrealistic scenarios, and I think, in retrospect, considering these scenarios, I think subtracted a little bit of credibility to the study, and I would have, I probably would have, even if I included, maybe I would include just one for the sakes of showing, but nothing else. Unfortunately, they went into a stabilized world model 2, um, and in this model, it's characterized by introducing birth control and better technologies for food and industrial production in 1975 on the left simulation, and 2000 in the right side simulation. Um, and the outcomes of this is that pollution is kept in check, and resource depletion is curbed. But this 25-year delay in policy implementation, which is what they wanted to show, is the delay of implementing these policies, delay stabilization. So I think that was and those were the major scenarios run in the World 3 model. So let's shift gears a little bit and talk about the kinds of things, the kinds of topics that we're going to be discussing. And I want to start. I wanted to start the intuitive introduction of system dynamics by using some very simple examples initially. Um, and I'll talk about your bank account, your or my bank account, your personal bank account. I'll talk about your body weight. I'll talk about population growth, so we'll look at more of a collective variable. I'll talk about water in a lake and the global economy. Okay, so let's try to tackle these issues. Let's look at your bank account, and your bank account essentially, if you think about what you look quantitative for in your bank account, it's essentially the amount of money that's stored in your bank account. Okay, now that amount of money in your bank account is not a static variable. It's a variable that changes over time. It changes over time because you have inputs of money, and those may come through income or deposits into your account, but you also have outputs, and these can be expenses, investments, any other
any other money that comes out. And then internally within the account, you have essentially also inputs and outputs that are dependent on the amount of money that's there. And I want to make the distinction, and we'll make this more clear later on, about inputs and outputs that are dependent on the variable itself and those that are not. And for the most part, your income and your deposits may be, for the most part, may be independent. Your salary, it's not really dependent on the amount of money you have in your bank account. But if you look at other sort of, like interest and fees and charges, they're add or subtract from bank account, those might be dependent on the amount of money that you have. Now, if you add all these things up, what you have in there plus what comes out in minus what comes out, then you have an idea of how that bank account quantity variable is changing over time. Okay, so I want to keep that notion in terms of this particular example. Another simple one is your body, and the body weight is also another quantitative variable that you keep track of, and that is the body mass or your weight. Okay, now your body weight, again, not a static variable. It will have it be influenced by inputs, like food, and outputs like excretions or surgery. I don't know if you do a liposuction or something, or whatever it is. A little bit crass example, but there also will be these within inputs and outputs that are dependent on your body mass. Like your exercise or your diet. You and I have different body weights, and if you go out there and run 4 miles, and if I go out there and run 4 miles, the outputs are not going to be the same, just because it is that output is going to be dependent on the specific body mass, and I'm simplifying things a little bit, but you get the idea. Again, another system where you have a quantitative variable that's affected by inputs and outputs, and thus it varies over time. Okay. Next one, a little bit less individual, is population growth. So let's say you're looking at a city, a country, a state, or and your variable is the number of people. Okay. Well, number of people is not, or not, the population in city, state, country, whatever entity, it's not a static variable. It will be affected by inflows, and the inflows could be net migration, positive or negative. It could be a net migration into the location or out of the location, and the output of that, or the is deaths that are related to anything that has to do with accidents or just people dying naturally, and then there's of course the births and deaths that occur naturally within the system. Okay, so again, the balance of these inputs and outputs will give you the dynamic changes in population. Okay, and we're going to be looking at these in a fair amount of detail in this class, but I wanted to sort of plant in your brains the sort of the logic of this. Okay, this sort of adding inputs and outputs and trying to see how those change over time. If you look at water in a lake, it's the same reasoning. The quantity you're likely to look for is the volume of water in that lake. And that's affected by inputs, and primarily those are going to be rainfall. There might be other inputs as well, and there'll be outputs like infiltration through the ground. There'll be runoff discharges to rivers or to the ocean from the lake, and then there'll be primarily an output that depends on the amount of water in the lake, and that's evaporation. So the evaporation depends on the amount of water in the lake. So if I want to keep track of this quantitative variable of water in the lake, I need to look at all these inputs and outputs and see how they shake up. Okay. Let's look at agricultural production, another one. So in this case, the quantitative variable should be, would be the agricultural products, and this could be, tons of corn or tons of wheat that are produced or that are present in a farm or in a state. Again, it depends on the system, and there'll be inputs. Inputs such as land and fertilizers or outputs, which is the amount of food that's generated, that's produced, and it's driven, it's sold to the markets or it's distributed to some supply chain. And then there's the decay or the loss. A fraction of the crops are lost to naturally to weather issues or to decay, natural decay. So again, the balance of these inputs and outputs will tell you a little bit about how agricultural production will evolve over time. Want to move into something bigger and better? Let's look at the global economy. Um, well, I sort of put this in there, but I was just kidding. We're really not ready for this one just yet. So let's not get ahead of ourselves. And there's a useful lesson here. So we need to start small and start by looking at small systems. Your body weight, your bank account, population of a small system, and see how that changes understand those before we move on to understanding larger systems. Okay, so let's just not get ahead of ourselves. I threw it in there just to generate a reaction. Now, of course, you can pretty much appreciate that these systems are not independent. So if you look at at water and energy and other issues, they're connected. And so if you have let's take the population system that we just looked at, and we looked at the water in the lake, other system we looked at. And we can think of these two systems interacting. So for example, the volume of water, the availability of that water, if the water feeds the population, um, it will have an impact on the health of the people, which will affect births and deaths. So if you have good quality water, plenty available, you have capability of having more births. But if you have little water available or poor quality, then you have more potential for death. So there's a connection between these two systems through health. There could be another connection. The number of people affect evaporation through essentially development. More people, the more roads, the more infrastructure you need. That affects that decreases the evaporation, the natural evaporation of the system, and you sort of alter the cycling of water. Okay, so you generate a balance there. Um, and other events such as excessive runoff, natural disasters of flood can affect, have an impact on creating additional deaths in the system that will affect population. So you can see how these systems become connected, and they're not really independent or completely independent of each other. And part of our job in this class is to find not only what these connections are, but how we quantify them. Okay, so we're going to be looking at these. And we can actually connect more systems. Let's take the two systems that are connected now, and then look at another subsystem that we looked at, the agricultural production, and we can say, well, um, the availability of water through either infiltration or runoff will affect the land availability for it. So, for example, if you flood a piece of land, it won't be available for harvest of a crop, and you sort of affect agricultural production. The amount of food feeds directly into the number of people that can be supported. So that's another connection between these systems. And the variety or the ability of agricultural production to grow may attract or detract migration. And that's a common problem in many countries where mass migration, mass migrant workers move between one country and the next, or one city and the next, to work on the fields and agriculture. It's a big interaction that happens worldwide. So so you can see that how these systems start connecting, how the influences, the mutual interactions, and these mutual influences are not trivial to predict offhand. And um, this is one of the reasons why we need modeling. So my pitch for why do we need modeling? First of all, we need to be quantitative, and in order to design effective policies, we need to understand quantitatively what's going on. Um, we need to be able to forecast, even if we're wrong, and more forecasts are wrong. The ability to forecast does point you in the direction of a trend that might enable you to launch a policy, or to implement a policy, or to make decisions that are important. I think another key use of modeling is assimilating data. So there is data that's collected, and models allow you to use that data to essentially analyze it and extract results. And anything from the simplest, like a linear regression, which is a tool that most of you might be familiarized with. That's a model in itself. Um, and models are really thinking aids. Okay, in this class, for the most part, we're not going to be looking to models as predictors, but more as thinking aids. And one piece of advice that I give you now is that it is best to never use the word prediction when you refer to a model, because you're going to be wrong no matter what. But actually, models are not really intended, or at least the models we're going to be discussing here, are not intended to predict. They're intended more to help us think, to analyze data, to forecast. And forecast has a big uncertainty to it that we'll discuss. And models give us the ability to be quantitative, but not really to predict. So I want to sort of take that word out of the vocabulary in this class right now, um, as a piece of advice. Okay. Now, for this class, we're going to be using a piece of software that's called Vensim, and I've already asked you to download it and install it, and we'll spend a couple of sessions learning how to use it, and using it to set up our models. But the gist of it is that it's a tool that's easy to use in assembling and running system dynamics um, models, and as well as analyzing the simulation results. Okay. Now, it's not the only piece of software that's available, but it has, in my opinion, it has a very simple interface that's easy to learn very quickly, and it's also free of charge for classroom use, and that's a big criteria right there. So I'm not going to deny that, and you can look at some background on the tool itself here for some history and background of the tool, and we're going to be looking at that more closely. So we're getting to the end of this lecture, and so I want to look ahead at what we're going to be doing next. Next, we're going to be formally introducing the discipline of system dynamics modeling. So we're going to be, looking at this modeling concept from a little bit more formally, and more accurately. We're going to explain the purposes of modeling, so a little bit more detail of what we explained today, and we're going to work on understanding the components of a system dynamics model, um, and gradually building a system dynamics model. So we're going to be looking at these systems that we've described: water, food, energy, population, and we're going to gradually start building simple system dynamics models, and then more complex. So hopefully this would allow us to get a grasp not only on the modeling technique itself, but also as to how integrating these pieces through modeling will shed some light on the questions of sustainability, which we will be posing continuously. So that is pretty much it. I am going to, like I said, I'm going to upload well, actually, if you've seen this, I've already uploaded it, but this lecture will be uploaded. It'll be there on the Dropbox folder in our Facebook page for you to see and you to look at. You can go back and forth, and you can ask any questions on the discussion forum. So it's been a pleasure, and I'll talk to you next time. Thanks very much. Au revoir. Enjoy the rest of the week.